All right, today we're going to work on our projectiles worksheet. Number 1 says we have a ball kicked from 18 feet per second from a cliff 80 feet high. How far from the base of the cliff will the stone strike the ground? So I'm sitting here on this cliff. I'm 80 feet in the air from here to here. I'm kicking the ball off this direction, so my initial velocity is 18 feet per second. The ball is going to do this kind of thing until it hits the ground down here. This is my ground. We want to know what's my change in position going this direction. That's my unknown. We know this is all horizontal to start. I'm not at an angle. This is kicked horizontally. So that is all Vx. This is my change in position in the y. Depends whether we count this is 0, that is 0, negative. We'll decide in a minute if we need to know any of that. Hasn't really told us. Acceleration is always acceleration due to gravity when we're a projectile. And since we're doing feet, it's going to be 32.2 feet per second squared. And it's pulling me down, so I'm going to make that negative. So really what I'm trying to do is say that delta x is what I'm looking for, is Vx times t. I have the Vx, I don't have the t. So for the t, I got to go look in this y direction. How long did it take me to fall that far is the same time it takes me to travel this far out horizontally. Okay, so if we look at this, we know the acceleration, we know my change in position. So let's look at my equations. Right, I only have these 3 things. I'm looking for time. I know the initial velocity in the y. Didn't really tell me, I didn't write it down, but if I'm going all horizontally, my initial velocity in the y is equal to 0 because I'm not moving up and down. So I have that. I'm looking for time. I have acceleration. I have my change in position. So I know exactly how far I'm going. Okay, so that's what I'm going to use. My delta y is VIYT plus 1/2 AP squared. Okay. When I do this, I know the initial velocity is 0. Okay, so now I'm going to solve for t. So I'm going to multiply by 2, so 2 delta y. Then I'm going to divide by a. Then I'm going to take the square root, and that should give me t. So I've just solved this equation for t. Now this is square root of 2 times my change in position y. And if I start up here, I'm actually going down 80 feet. Okay, so I'm going to make that a negative because I'm counting this as my initial spot. Okay, and I'm going to head down. So I'm going to go down this negative 80 feet, going down, and then the negative 32.2 feet per second squared. And I get down here. And now I get my calculator out, solve all this. And we have the square root of 2 times negative 80 divided by negative 32.2. And we have this 2.2 seconds. Now we can take that 2.2 seconds and we can use him up here because time is the same in both directions. So my change of position is Vx, which is 18 feet per second. I'm going to multiply that by my 2.2 seconds. So 18 times 2.2, and I get 39.6. My changing position is 39.6 feet, in which the seconds cancel out. And there's number 1. If we look at number 2, a bullet is fired at an angle of 45 degrees. Neglecting air resistance, what is the direction of acceleration during the flight of the bullet? Okay, so bullet is fired at an angle of 45 degrees. 45 degrees. It's going to do all this stuff. This is what is the direction of acceleration? Well, here's the Earth. It's pulling down. Force of gravity is pulling my object down, so my acceleration is going to be going down. So, if you like those kind of questions, easy peasy. Oh, keep it on the screen, that would help, huh? Okay, number 3, an egg is thrown horizontally off the roof, which is 60 meters high, with an initial velocity of 6.5 meters per second. How long does it take to hit the ground? How far does it go in the x direction? You notice this is exactly what we just did in number 1. All we're going to do is replace this 80 with 60, but now it's meters, so we're going to have 60 meters. We're going to replace the initial velocity, and instead of 18, we're going to have 6.5 meters per second. My acceleration is now negative 9.8 meters per second squared, and we're going to use this same equation, and we're going to use this same equation. So I'm not even going to look at 3. I'll let you figure that one out. It's the same as number 1. Okay, so that one isn't hard. All right, let's look at number 4. In number 4, we have a bullet this being part of an angle of 60 degrees, an initial velocity of 600 feet per second. What is the initial velocity in the horizontal and vertical directions? What is the maximum height reached by the bullet? So now we have this thing taking off at 60 degrees. Okay, it's fired at 600 feet per second, so my initial velocity is 600 feet per second. It's going to go way up here in the air somewhere, and it's going to head back down like this out. Okay, not a great problem, but it all works. What they want to know is what is my velocity in the x and my velocity in the y initially. So this is part A. So initial velocity in the y. Y is the side opposite. Opposite goes with sine, so it should be the hypotenuse times the sine of the angle, which is 600 feet per second, times the sine of 60 degrees. And then in the x direction, my velocity in the x direction, this is the side adjacent, so that goes with cosine, so it's just the hypotenuse times the cosine of the angle, which is 600 feet per second times the cosine of 60. And then again, we just go into our calculator. We go 600 sine of 60, 600 cosine of 60. Then we get 519.6 and 300. Let's just call that 520 feet per second. And this one's equal to 300 feet per second. And then in part B, what is the maximum height reached by the bullet? Okay, so if we're looking at part B, as we go up here to the top, we're looking for this change in y. As we went up there, we know at the very top, my final velocity in the y direction is equal to 0. My velocity next is still 300, but I'm going to look in the y direction because I'm going up and down to see how high I went. Okay, we know the acceleration is always equal to 32.2 feet per second squared, and negative because it's pulling me down. All right, so again, we have my initial velocity, my final velocity, my change in position, my acceleration. We're looking for maximum height. Okay, they don't tell me time at all. So if you look over here, the only equation that doesn't have time, the one I don't have showing, is this guy here. So let's use him. So we know that Vf squared equals, and we're talking in the y direction, Vi squared, also in the y direction, and plus 2 times the acceleration times the change in position. We know my final velocity is 0, so that goes away. So now we're going to say negative Vi y squared, and we're going to move that over, divided by the 2a, is equal to the change in position. Now we just plug our numbers in. So we have negative VIY, which was 520 feet per second, 520 feet per second, and all of that is squared, all over 2 times negative 32.2 feet per second squared. Then we get out our calculator and see what we end up with. So we have 520 squared on top. Okay, and then that's a negative, so we have negative of that answer divided by 2 times 32.2. Hey there.
Well, I saw you did amazing.
Okay, sorry. We were working on this problem and then tutoring started and a bunch of people walked in. So here's the finish. We were just calculating this. We had done the whole problem. We were solving for how far, how much time. Yeah. Sorry. We were looking for, I don't even know what we were looking for anymore. What is the maximum height reached? Here we go. Now we're back on track. What is the maximum height reached? Delta y. So we were putting these numbers in. So we had 520 squared, which is this thing here. Then we needed to divide that by, since there's a negative on top and bottom, they will cancel. So I'm just going to ignore those. 2 times 32.2. Now we get 4,200, basically, or 4,199. 4,199 feet. Okay, that's how high I went. Change in position, we went up in the air. All right, I'm going to call that good for now. I'll try to come back, maybe do 5 through 8 on another video.